In this sliding block problem, we have a frictionless system, and it's shown as with all these masses connected by ropes. We assume that the rope is massless, assume the pulley is massless, and there's no friction anywhere on the rope or on the ground. We assume the rope doesn't stretch. The question is, what's the forces in all these ropes connecting all these masses? So this is a horizontal surface, and this is an inclined surface with the angle theta relative to horizontal. So we'll pause now. We're going to solve for all the, so 3m, m, 2m, m, 2m, solve for t1, 2, 3, and 4. So now I want to, so here's the answer. So here's the answer. So t1 is mg sine theta, t2 is 4/3 mg sine theta, t3 is 2 mg theta, and t4 is 4/3 mg sine theta, and it's accelerating at g theta over 3. So if you have those answers, that'd be great. If you don't, otherwise we can talk about how we might want to approach this problem. When we have this problem like this with multiple things moving, you may be just tempted to just jump in and try to solve for a t1. But if you circle any one or a group of them, you'd find you'd have a force acting on it or multiple forces acting on it, an acceleration, which you don't know what it is. You'd have more unknowns than you can deal with. So often when you have more than a collection of things and you want to try to find internal forces, you have to sometimes understand that we need to understand about the global motion of each of the system in its entirety. And so if we divide something into groups, we want to think about, first of all, are they moving together? Do they have the same acceleration? Well, these three blocks have the same, because of what we were told, they have the same acceleration, magnitude, and direction. But they're different than these two blocks. These ones have acceleration horizontally. These two blocks have an acceleration going down the inclined surface, frictionless inclined surface. So it makes sense so if we group them all together, we'd have different accelerations because the vectorial direction of these would be different. So I want to just look at those groupings first. So if I draw a free diagram of these three systems, so draw all the blocks, all the forces acting on them. I have gravitational forces acting on all of them. I have normal forces acting on all of them, and I have this tensile rope force pulling horizontally. And it's called T3. So those are the forces acting on it. Now we got to think about accelerations. I have no acceleration in the y direction here, going up and down, but I probably have an acceleration horizontally. So since I know that's 0 and that's what I want to solve for, I probably want to draw my coordinate system such as that, like that. So now if I solve for some of the forces in the x direction, where I call it positive x in this direction, well, some of the forces is mass times acceleration. All of these are accelerating together, the same acceleration x magnitude, and the mass is the sum of each of the masses. That elements in there all moving together. And then the other force, and then that equals the sum of the forces acting in the horizontal direction. The only force I've shown here in the horizontal direction is a positive T3. So now that I can solve here for AX is that value. And then we think of the other subsystem. Those parts are also accelerating parallel inclined plane. So if draw a free body diagram, so I have gravitational forces, normal forces, and my T3 force. Same T3 force pulling there is pulling there. Directionally different, but same magnitude. And then I have this, they're on the theta. So I have no acceleration perpendicular to the surface, but I have some acceleration potentially parallel to the surface. So that's a good coordinate system to pick. So for this one, for this free body diagram, that's the coordinate system that applies. So I'll call the positive x in this direction. So that's mass times acceleration in the x direction. So that's the sum of all the masses that are in there. And then forces, I have the vectorial component of these gravitational forces are acting in this positive x direction. Okay, and they're related to vectorially, you can find that they're the magnitude of the cumulative gravitational force times the sine of theta. And another force acting is in the minus x direction is T3. So I can take that and solve for a sub x here, and I know that this magnitude here and this magnitude are the same. Okay, so I can substitute this a sub x in for this. Okay, and I do some algebra, and I can solve for T3 from here. So right from there, I get my T3. So that's 2mg sine of theta. Now I can back substitute into here. I know I get I can solve for a sub x. So if I solve for a sub x, I get just algebra g sine of theta over 3. Now I have a sub x. So now I know how this one's moving and how this thing's moving, and I also know T3, the interface force between those blocks. Now it's a matter of just going back. Since I have acceleration, we can start tackling them. It's often easier than if I think about this block right here. I know it's acceleration. There's only one other force acting, so this might be a good system to look at right here to try to find T1. So if I do a free body diagram block number 1, I get my forces acting on it. T1's my unknown. Normal and gravitational forces. Some of the forces in the positive, I'll make the coordinate system be the xy because I know no acceleration this way, which I now know the magnitude of. So some of the forces is mass times acceleration x direction. The only external force acting is T1, so I can solve for T1. Similarly, I can now do B or C. So let's just jump to C. I know T3. I want to find T2. So free body diagram, block C. Very similarly. So sum of force x direction positive, mass, acceleration, and I got a T3 minus T2, and I can solve for T2 is 4/3 mg over sine of theta. Then I could also do, if I want to find T4, I could do here or here. So it might be easier to take the end one, block E, free body diagram block E. I have my T4 force on it. I know my acceleration in x direction is this way. Acceleration y is 0. I have gravitational force of 2mg, normal force perpendicular to the x direction. So if I sum the forces in the x direction here, I get mass times acceleration in the x direction. I got a minus T4 acting on it, and this vectorial component of the gravity, 2mg sine of theta. So solving for it, I can get T4. So now I can also then do some double checking. I could circle around some other ones and make sure everything makes sense. But so this is the solution for all the internal tensile forces on the rope.